and welcome to the third Volkswagen Communications Network service release covering the air conditioning system. Air conditioning is no longer a luxury item in today's automobiles. It improves the total driving environment and increases passenger riding comfort. The air conditioning system has three principal functions. It cools the interior air, removes moisture or dehumidifies the air, and circulates the cool, dehumidified air inside the car. There are three main sources of heat inside the car. The first is radiation. The sun's rays on the body sheet metal, the roof, and the glass heat the air inside the car. Heat also radiates from the road surface when the car is parked or not moving in traffic. The second is conduction. Heat from the engine, transmission, and exhaust system is conducted through the firewall and the floor. And finally, there's convection, which allows heat into the car through an open window or door. Added to this is humidity, which is simply moisture in the air. Any air coming into the car brings moisture with it, making the interior even more uncomfortable. The air conditioning removes the heat coming from these sources, providing a comfortable interior for the passengers. In this program, we're going to cover air conditioning system operation and service. We'll start with principles of operation and refrigerant circulation. During the hands-on demonstration, we'll start out with basic checks and system performance checks, then go on to our service procedures. As we go through this program, remember, our intention is to familiarize you with basic air conditioning system operation and service procedures. Before we actually get into the air conditioning system on the car, we need to review a few fundamental principles. They're things you're probably familiar with already, and they help explain how an air conditioning system works. One of the easiest examples we can use to explain air conditioning is to boil water. Principle number one is that heat always goes from the hot object to the cold object, in this case from the burner to the water. When the water boils, it becomes steam or vapor. This is called a change of state from a liquid to a vapor or gas. Turning the water into vapor requires about 4 times more heat than simply bringing the water to a boil. The steam absorbs this heat. So there's a large transfer of heat when a change of state takes place. That's principle number 2. Since the air is much colder than the steam, the heat goes from the steam into the air. When all the extra heat is lost, the steam changes state. It condenses into drops. In other words, it changes back into water. A car air conditioning system uses the same basic principles when turning liquid into vapor or vapor into liquid, with large amounts of heat being transferred as each change of state takes place. With this basic process in mind, let's look at the way pressure affects temperature and temperature affects pressure. Again, we'll use the example of water to demonstrate this. As you know, water boils at 212 degrees Fahrenheit at sea level. The boiling point is lower if air pressure is lower, such as at high altitudes. In Denver, for example, which is above 5,000 feet, the boiling point of water is about 207 degrees Fahrenheit. By the same token, increasing the air pressure raises the boiling point. For example, a radiator pressure cap is a device to raise the pressure inside the cooling system. In a system operating with a 15 psi cap, the boiling point of the coolant is raised to over 250 degrees Fahrenheit. That's principle number 3. Higher pressure means a higher boiling point. Lower pressure means a lower boiling point. The same principles we've just seen demonstrated with water also apply to the air conditioning system refrigerant R12. The reason R12 is used for air conditioning is because it can absorb and dissipate large amounts of heat quickly, but it also has some rather odd characteristics. R12 refrigerant boils, that is, turns into vapor, at minus 21 degrees Fahrenheit. This means it would normally be impossible to use in an air conditioning system. But by pressurizing the system, the boiling point of the R12 can be raised. This chart shows how the temperature of R12 rises as pressure increases. A useful point for diagnosis and service is that temperature and pressure are quite close throughout the range, as you see here. Change of state and the relationship between pressure and temperature are important to air conditioning system operation. Different components in the system cause the changes in state by controlling pressure and temperature. Let's look at these components first. then turn to system operation and refrigerant circulation, keeping our basic principles in mind. The first change of state takes place in the evaporator. The refrigerant here is under low pressure, and low pressure means a low boiling point. So the refrigerant boils and turns into vapor. Because heat always goes from hot to cold, the R12 absorbs large quantities of heat from the passenger compartment. The second change of state, this time from vapor to liquid, takes place in the condenser. The R12 enters the condenser as a high-temperature, high-pressure vapor. The condenser also works just like a radiator. The refrigerant loses large amounts of heat to cooler outside air. So the vapor has condensed to a liquid when it leaves the condenser. Now it's time to look at a complete cooling cycle and see how these two components work together with the compressor, the receiver dryer, the expansion valve, and the thermostatic switch to complete the air conditioning refrigerant circuit. Let's start with the low pressure vapor coming out of the evaporator. The vapor has absorbed the heat from the car's interior. The compressor draws this vapor from the evaporator on the piston's downstroke and compresses it on the upstroke. As its pressure rises, so does its temperature. The refrigerant is pumped to the condenser as a hot, high-pressure vapor. As the compressor pressurizes the refrigerant and circulates it, it also pumps refrigerant oil through the system to lubricate the compressor and the seals. The air passing through the condenser fins is much cooler than the R12 vapor. As heat is given off to the air, the vapor cools and condenses to a liquid. It is now a high-pressure liquid. The liquid R12 now goes to the receiver dryer. It has two functions. First, it acts as a refrigerant storage tank because the amount of refrigerant required by the evaporator can vary, as we'll see. Second, a desiccant inside the receiver dryer absorbs small amounts of moisture. Most receiver dryers also have a sight glass to let you check system refrigerant charge. From the receiver dryer, the refrigerant flows to the expansion valve. The expansion valve meters the flow of refrigerant to the evaporator. By doing so, it controls the temperature of the evaporator. Too little refrigerant flow results in insufficient cooling. But if too much refrigerant enters the evaporator and it gets too cold, moisture from the air can freeze on the coils and block airflow. The expansion valve has a diaphragm and spring that control the size of the opening, or orifice, through which the R12 enters the evaporator. The diaphragm is connected to a sealed capillary tube attached to the evaporator outlet line. When the outlet line becomes warm, the gas in the tube expands. It moves the diaphragm and the orifice opens, allowing more refrigerant into the evaporator. As the outlet line becomes colder, the gas contracts and the spring moves against the diaphragm to close the orifice and reduce refrigerant flow. Now, let's bring everything together that we know about R12 refrigerant. As it goes through the expansion valve, its temperature and pressure drop. As it goes into the evaporator, it starts to boil into vapor. Remember our example of boiling water. As the water became steam, it absorbed large amounts of heat. Now recall that R12 boils at minus 21 degrees Fahrenheit. So even though the R12 isn't as cold as that, it's cold enough to absorb a lot of heat from the passenger compartment. As the R12 changes into vapor, the blower fan draws air across the cold evaporator coils and directs it out through the dash vents. Moisture in the air condenses on the evaporator, and the water is drained out of the car. The vapor in the evaporator is pulled back to the compressor, and the cycle begins again. Air conditioning systems using a cycling compressor have a thermostatic switch to regulate compressor operation, as well as the expansion valve to control refrigerant flow. The switch uses a capillary tube that measures evaporator temperature. It's wired in the compressor relay circuit and either completes the clutch circuit or opens it to prevent evaporator freeze-up. Now that we've followed system operation through all its phases, we can move on to our service checks. For safety's sake, perform all air conditioning service in a well-ventilated area. Always wear eye protection because the refrigerant is under pressure and it can cause permanent damage to your eyes. Finally, avoid working around open flames because poisonous gas can form if R12 comes in contact with an open flame. Begin by making a visual inspection of all components. check the condenser for blockage or damage to the fins that could affect airflow and heat transfer. Inspect refrigerant hoses for damage and check all connections for obvious refrigerant oil leaks. Check the blowout plug on the receiver dryer. If high side pressure has been excessive, the plug will be blown out, causing a complete loss of refrigerant charge. If the blowout plug has opened, check the operation of the cooling fan to make sure it's engaging at the appropriate signal. If the fan doesn't cool the condenser, excessively high pressure can build up on the high side. Split, leaking, or disconnected vacuum hoses or a leaking vacuum tank can affect the operation of the air doors. This may affect cooling performance, even if the rest of the system is working properly. Check for refrigerant leaks at the compressor clutch seal. While you're there, check the drive belt for wear and correct tension. While you're under the car, check the water drain hose to be sure it's not blocked. If water can't drain, the customer will complain of water on the carpet or water being blown out of the vents. Those were our basic visual checks. If you found nothing out of the ordinary, your next step is to make system performance checks. You need a pressure gauge set to make these checks. With the gauge set, you can test high and low side pressures and refrigerant flow. You can identify the high side gauge by its pressure range. The low side gauge has a much lower pressure scale, and it also has a vacuum scale. With the engine off, remove the caps from the service ports. Be sure both valves are closed on the gauge set. Then connect the high side gauge to the discharge fitting. That's the one between the compressor and the condenser. Then connect the low side gauge to the suction fitting. That's the one between the evaporator and the compressor. If you're using a charging station to conduct your system performance checks, follow the manufacturer's instructions closely. Once the gauges are connected, check the pressure readings. They should both be equalized above 50 psi. This is static system pressure. It indicates there is adequate refrigerant charge to conduct the performance checks. Inside the car, open the air vents on the instrument panel. Place a thermometer in the center vent and close the windows and sunroof. Now, start the engine. Set the blower speed to high, move the temperature lever to the coldest setting, and press the AC switch. The compressor clutch should engage. Run the engine at 2,000 RPM for 5 minutes. Then observe the sight glass on the receiver dryer. A clear sight glass is what you want to see. Foaming refrigerant or a constant stream of bubbles indicates a low refrigerant charge. Occasional bubbles are okay. Remember, this isn't air in the system, but refrigerant vapor. Low pressure readings on both the high and low sides will confirm a low refrigerant charge. When checking your readings, don't forget that ambient temperature and humidity can cause normal readings to vary. An acceptable range on the low side is from about 15 to 35 psi, and from about 150 up to 300 psi on the high side. Naturally, ambient temperature and humidity affect outlet air temperature as well. If the system is functioning correctly, temperature at the vent will usually be between 36 and 48 degrees Fahrenheit. If the system does not pass these tests, refer to the repair manual microfiche for diagnosis and troubleshooting information. Some repairs or component replacement may require the system to be discharged, evacuated, and recharged after you have completed the work. In the final part of the program, we're going to see how to perform these operations. With both gauges connected and the valves closed, the best way of discharging the R12 gas is to let the center hose vent through the shop exhaust system. Then slowly open the high side valve to start purging the system. When most of the refrigerant is purged, open the low side valve to complete the discharge process. The reason the low side isn't discharged first is because it's open to the compressor crankcase. If you discharge refrigerant on this side first, you'll pull the refrigerant oil out along with the refrigerant. This can cause damage to the compressor when the system is started up again. When the gauges reach zero, the system is discharged, and you can perform any necessary repairs or replacement of parts. Once you've completed your service work, you have to evacuate and recharge the system. Evacuation means first ensuring that all moisture is removed from the system. Even though the desiccant in the receiver dryer is designed to remove moisture, when the system is open, moisture can enter. It is critical for the system to be absolutely moisture-free. Remember how low the refrigerant temperature is on the low-pressure side of the system. Even the smallest amount of moisture mixing with the R12 can freeze at the expansion valve as the temperature drops. This will block the orifice and stop refrigerant flow. Refrigerant also reacts chemically with moisture to form hydrochloric acid. This is highly corrosive and attacks all metal parts and components in the system. It also forms sludge, which can block the expansion valve, condenser, or evaporator. A vacuum pump is used to evacuate or remove air and moisture from the system. The vacuum pump does this by using the same principle we saw earlier. Low pressure equals a low boiling point. It creates a vacuum in the system, usually expressed as inches of mercury. Here you can see how reducing the pressure lowers water's boiling point far below normal. At a vacuum of 29.3 inches of mercury, water boils at 70 degrees Fahrenheit. So ambient air temperature can boil the water, and the vacuum pump draws the vapor out. To evacuate the AC system, connect the center hose to the vacuum pump. Open the valves on the gauge set and start the pump. Once the correct vacuum level of 29 inches is reached, run the pump for 30 minutes to remove all the air and any possible trace of moisture. Hold the vacuum in the air conditioning system by closing the valves before you turn off the vacuum pump. Now check the low side gauge reading. Vacuum should not drop more than 1 inch in 5 minutes. A rapid rise to 0 indicates a leak in the system. After all the air and moisture have been removed from the system, you can charge it with fresh refrigerant. First, check the repair manual microfiche for the proper refrigerant charge. Remove the center hose from the vacuum pump and attach it to a full can of R12. Open the valve on the can and briefly loosen the center hose connection at the gauge set to purge any air from the hose. First, charge the system with R12 with the engine not running to prevent damage to the compressor when the air conditioning is first turned on again. Invert the can of R12 and open the high side valve. When the can is inverted, liquid refrigerant flows into the system. As we said, this must be done with the engine not running. Never run the engine with the high side valve open. The pressure generated on the high side can cause the can of R12 to explode. When the first can is empty, close the high side valve and disconnect the can. Connect another can of R12 and purge the center hose as before. Now start the engine. Set the controls to maximum cooling and run the engine at 2,000 RPM. After opening the low side valve, hold the can of R12 upright. This allows the system to draw refrigerant vapor in through the low side. To make the charging process go a little quicker, you can immerse the can of R12 in warm water. This raises the temperature of the R12, and as you recall, higher temperature means higher pressure, so the vapor enters the system more easily. The water shouldn't be more than 95 to 100 degrees, and you should never use an open flame or any kind of concentrated heat to warm the can. When the system has the recommended charge capacity, check the center vent air temperature to see that it's within the recommended range. Also, make a final check of the sight glass to be sure it's clear, with perhaps only occasional bubbles. That concludes our service presentation on air conditioning systems. As we said at the beginning, our objectives have been to introduce basic operating principles, illustrate how the components work together, perform basic visual checks of individual components, carry out system performance checks, and demonstrate the basic service procedures of discharging, evacuating, and recharging the system. For more complex diagnosis, service, and repair procedures, consult the repair manual microfiche to be sure you're staying up with the latest in advancing technology.